Hi guys, this is Aaron Harper. I am doing a presentation on link budgets because there seems to be a bit of a confusion as to exactly what a link budget is and what it does for you. This presentation will be an introduction to it, and we'll highlight things like what a link budget is, why you need it, and what the parts of a link budget are. It's part of at least a 7-part series on link budgets, how to do them manually, what software, and so on. First of all, what is a link budget? Okay, the clicker isn't working. Come on. Pardon me. It does help to have the focus in the right window. Link budgets. A link budget is the accounting for all the gains and losses from the transmitter through the medium, regardless of what it is, and all the way to the receiver to the telecommunication system. What that means is that you not only need it for satellite communications, you also need it for things like fiber optics. You need it for terrestrial radio communications and so on, because it takes into account, for example, the transmitter, the losses in the transmission line, the transmitter power, losses in the transmission line, gain of the transmitting antenna, the losses over the distance that is being transmitted, then the gain of the receiving antenna, the losses in the transmission line going to the device, the gain of the amplification, the losses of the switching and for example noise that the amplifier will introduce, the sensitivity of the receiver, all the way down. It's like a budget you would do for a business, in that you have credits and debits. In this case, you have positive dBs or decibels, which are your positive end of things, like the gain of a transmitter or a gain of a receiver or preamp. You also have areas where you deduct. For example, the loss of a transmission line, the noise where the signal might get swamped by the noise floor, or the biggest one will be the loss of the signal through space. If you think about it, if you have a candle really close, you can read by it. Power goes out, you light a candle, read a book because internet's down. But if you put that candle on a mountaintop, you might not even be able to see it. The difference is something called the inverse square law, and that means that as distance increases, the amount of power is received is the inverse square, so therefore much less. And it's not a straight one-to-one relationship, it's logarithmic. But the free space propagation loss is the largest loss you will have in a link budget. And that's what you need to offset by using things like receiver sensitivity, preamps, and the transmit power. But a link budget will allow you to see if your system will actually do the job. It's very, it allows you to do it on paper before you do it on, in atoms and scratch your head and why you wasted the money. But the first part of this series will be the intro to link budgets, which is what we're covering now. But again, a link budget is the accounting of all the gains and losses from the transmitter through the medium, free space, cable, waveguide, fiber, whatever, to the receiver in a telecommunication system. Naturally, since we're doing aerospace, this is primarily going to focus on a satellite link. But in the transmission and receiving portion of a satellite link, there's still the waveguides, the couplers, the switches, and so on. So it's not all going to be focused on the propagation loss. Now, normally there are two link budgets. especially for satellite communications, one for your uplink and one for your downlink. You might wonder why you would do that twice. Now, the reason is because sometimes, in fact, most times, the uplink and the downlink frequencies are different. Excuse me. The uplink and the downlink frequencies are very, very different. In the case of the example which we'll use throughout these presentations, the International Space Station at the time used to downlink on a VHF frequency, in other words, about 145 megahertz. The uplink frequency was on the UHF band, which was about 435 megahertz. Now, the differences are not too great when you're dealing with those. But when you start hitting the microwave frequencies into the gigahertz range, for example, you start having a completely different characterization of the signal as it goes through space, as it goes through the atmosphere, and so on. So therefore, you have to kind of do it twice, or you're going to be making some assumptions. Now, since we're primarily worried about a satellite communication, and we're primarily worried about satellite reception, we're just going to focus on the receive side for the purposes of this video. Now, a link budget, like I said, consists of the following sections. The first one is the transmitting system analysis. That's the transmitter, the gain of the final amplifier of the transmitter, the link, the transmission line to the antenna, and the gain of the dish itself, or whatever kind of antenna that they happen to be using. There may be other pieces of equipment in there. For example, if you got a switch in order to turn things on and off or whatever, those losses also need to be taken into account. Now, we're not talking about a huge amount of loss here. In some cases, you might be talking about as little as 0.05 dB, which on a logarithmic scale comes to some, if I had to put a number on it, probably a thousandth of the signal, if not less. So really not that big of a deal compared to the rest. Now, the free space propagation loss might be and most likely will be, in the hundreds of dB. So in the grand scheme of things, not that huge, but you have to account for it, because when you're running fairly tight, it could be the difference between making it work and making it not work. And if you engineer the system based on zero on the connector losses, on switch losses, and so on, you might end up with a system that doesn't work in the final analysis. As I said, the second thing will be the free space propagation loss. The third is receiving system analysis, and it's very similar to the transmitting side, with the exception that you need to take into account a few other things. One of them is the noise figure, how much noise the sky has. Anything that's got heat, including the sky, has a certain amount of noise. It's what happens when atoms bump into each other. The result is that when you have this noise, if you have a very weak signal, you might not be able to pick it up. And hopefully it doesn't. You're not running that tight. But if you are, you still need to take that into account. You also need to take into account exactly how much signal your decoding mechanism needs, particularly for digital communications. Most of them, most of the digital communication modes are fairly robust. That's why they use them. But there's still a point where they quit working. You cannot get the amount of bandwidth you want in a signal that's too small. It's just the nature of the beast. The other thing, taking a step back to the propagation, the free space propagation, is you also have things like ionospheric losses. Certain times, especially during sunspots, you get excellent ducting of the signal. It creates a sort of almost like a waveguide in the atmosphere, which allows the signal to transmit from one point to the other without a whole lot of losses. People, with CB radios have been talking to Hawaii during those particular times. And ham radio operators, generally speaking, love it. But what it does for space communication, since we're not going across the atmosphere, we're going through it. That means that ionospheric duct actually presents a barrier to us. So that's one thing we need to take into account and make some minor adjustments. The other one is weather losses. Certain frequencies, especially as you go higher in the microwave bands, have a higher amount of attenuation, in other words, signal loss, than lower frequencies. Easy way to remember this is lower frequencies act like sound. They can go around corners, they can shoot through things. Foggy day, you can still talk to the guy across, you can still shout and be heard. As you go higher in frequencies, though, it starts acting more like light. Instead of going around bends and so on and so forth, it becomes line of sight. As with weather, for example, you might not be able to shoot through a cloud, especially with your higher frequencies into the what they call the Ka band or millimeter wave. But it's something to bear in mind. And each one, there are tables where you can look at the amount of attenuation based on your atmospheric conditions. But we'll go more over these things as the series goes to the next part. We covered all the issues regarding the receiving signals. But what we're going to be focusing on is a sample scenario where we have an ISS voice contact that we need to make at the frequency of their transmitter, which was at 145.975 megahertz. Unfortunately, that receiver is now inactive. It's no longer necessary, so they boxed up the transmitter. But it's a good exercise and a good sample of what is required. Now, in our scenario, we're going to have our receiving antenna at sea level, just to make the math a little easier. But in a real scenario, and I will point this out when we're doing the math, in a real scenario, you will have a little bit of extra altitude on top of sea level. For example, here we're about 1,500 meters above sea level. Almost 2,000 meters. But because of that, it changes the angle slightly. But just for the sake of this one, we'll be doing the math as though we were at sea level. Now, in our scenario, we're going to be looking at ISS at a 60-degree elevation above the horizon. And ISS, we're going to assume that ISS is at an altitude of 400 kilometers above sea level. That varies, and that's why the ISS, they have to reboost now and again, because with even the small amount of atmosphere up there, which is almost negligible, there is some drag, and as it slows down, it drops in altitude. So in a real world scenario, we would have to verify the altitude of the object we're trying to track. And as we go through the math, you'll see why these numbers are so critical. Again, VHF frequency 145.975 megahertz, 60-degree elevation. 400-kilometer altitude for ISS, and the receiver is at sea level. And that's the scenario we'll go through as we step through the scenario. Now, as far as the other pieces of information we will need for our scenario is what kind of equipment do they have? They had a Kenwood D700 radio, which was limited by modification to 25 watts, because 25 watts is what they wanted on ISS anymore, and they start risking interference with other systems. So we know for a fact that that was 25 watts. The gain, we're looking at a 6 dB gain antenna, but that is not necessarily accurate. Like I said, that particular system has been boxed up, so if it ever comes back online, the characteristics may be different, but it's another thing that we need to research in order to find the information. What we can assume from this is that the transmitter output power is 25 watts, which comes to a positive 24 dBm. That number will become necessary when we're doing a lot of the math. If we guess about the transmission line losses, we can probably put them at 0.05 dB. It's just a guess, but it's a fair guess. If we add another 0.5 dB for losses in the connectors, filters, and so on and so forth, again, it's a guess, but it's an educated guess. And then, as I said, antenna gain is positive 6 dB. Knowing that information, that is step one, is researching the information, and you can find this information on pretty much any website that has to do with that particular satellite. If it's a ham radio satellite, it's probably on AMSAT. If it's ISS, Friends of ISS, the website have got the most current information and probably the most informative. If you're dealing with something else, you can probably call up either the owner of the satellite, and get the documentation from them. Analytical Graphics Incorporated has got a fair bit of information about these things. If it's a military satellite, well, if you don't have the information, you probably don't need it. But step one is doing all your groundwork, all your research, and pulling all your information. Now, regarding the information, I don't know how to stress this enough. Watch your units. A lot of folks say, okay, we're at so and so many feet, so and so many miles, so and so many meters, kilometers, and so on. You can't mix your units here. Well, you can, but you won't get any result that makes sense. So don't do it. Keep your units the same. Either check it and recheck it front to back, or use units that consistently throughout. Me personally, I choose to use the metric system, and we will be using the metric system here in meters and kilometers. But again, make sure that if you're shooting for meters on one side, that you shoot for meters on the other. If you have kilometers on the one side, make sure kilometers are what you end up with the result. Otherwise, well, you're going to be sad and have to do it all over again. But the important part, and the step two after you've done all the research, is you need to find out, because the first step of this gives you all the information you need for the transmission subsystem. The second part is that you need to find out your propagation losses, and all of that has to do with the distance to the target. And for that, we need something called the slant range. And we will cover that in a later section. The third part is another piece of research for reception. If you're using NASA resources for reception, such as the DSN dishes, all that information is online and into PDFs. All you have to do is find the information on the NASA and JPL websites. If you're using things like software-defined radio, such as the EDITS research, USRP, or if you're like me and choose to use the cheaper varieties, the RTL information, the RTL SDR, the little TVB dongles, all that information is online, but you will need it before you start bolting things together. Because you'll need it to do the math first to see if it'll work. Otherwise, you're going to be sorely disappointed. But basically, that is what you need in order to do the job. Once you have the transmission side, the propagation side, and the reception side, you can put it all together, and that will be another section where we put it all together and evaluate to see whether or not we can go. And if we can't, see where we can adjust it. Now, after we've done all this, and I'm sorry, it will be after we've done all the work the hard way, we'll cover some of the software that makes it all possible. If doing all this work manually is not for you, you might want to go ahead and skip to the part where we talk about all the software. But in my experience, it's always good to do the work manually first, at least once. That way you can sanity check the figures that the software gives you. Because we all know garbage in, garbage out. If we put in a piece of information wrong and we get something that looks a little strange, we need to have the education in order to look at that and say, okay, this does not meet the sanity check. So that's why we're doing it manually first, and then we'll go through software. But that's it for now. Thanks for watching. And part 2, we will go through the transmission system, and that'll come up next.